We are repeatedly told that one of the keys to a meaningful life is understanding why we do the things we do. Why is it then that so many myths about how our brains function persist? Why are our own minds so often misunderstood by their inhabitants? Is it just that the brain is too complicated? Will we ever grasp how it works, or is that understanding simply beyond our intellectual abilities? Well, these are the questions that this new series is all about. We're going to address many of these questions in our brand new series, Brain Myths. We're going to talk about things you think, or you may think, that nobody can argue that this is the case when it comes to how your brain functions. But you will see throughout this series that we will debunk many of these myths. Now, today's episode is entitled Are Big Brains Smarter? Because that's one of the myths, but we're not going to answer only this question. We're going to start with the very first, is your brain perfectly designed? And then we're going to move on to the title, Are Bigger Brains Smarter? So welcome to your new series, Brain Myths. This is your host, Danny, and this is English Plus Podcast. Now, just let me remind you that you can find the transcript of this episode on my website, EnglishPlusPodcast.com. And when you go there, you will find that there's a lot of content that you can read, listen to, watch, to learn and have fun. And that is basically what English Plus is all about. And, of course, there's an extra thing. While you're in there, you'll find that there is exclusive content only for my patrons. And to access all the content, you can simply become a patron on Patreon. The link is in the show notes. It will take you to my Patreon page, where you will unlock access, first of all, to all the premium episodes that I post for every single free episode I make. So for every single free episode you hear on English Plus Podcast, there's another premium one that is available only to my patrons. And here I'm not talking about the same episodes. No, we have different types of episodes, different series that I'm sure you will enjoy and learn from a lot. So with that being said, let's not waste any more time and let's start with our very first question for today, or actually our very first brain myth for today. Is your brain perfectly designed? That's what we're going to talk about next, so don't go anywhere. I'll be right back. Many people have called the human brain, with its 86 billion neurons and hundreds of trillions of connections, the most complex thing in the universe. But with all its complexity, power, and beauty, it can also be messy, random, and inefficient. But don't be disheartened with that. You will figure out something very important, that when we debunk the myths, when we just cut through those various myths about the brain, you will find that the facts are often more amazing than any fiction we could invent. So to talk about this myth, let's first talk about the complexity of the brain. Well, the most basic myth about the brain is the deep-seated intuition that the brain is a masterpiece of neural design. The brain is highly complex, can't argue about that, but it is simply the end result of millions of years of evolution. Every complexity in our brain arose from a very long history of tiny tweaks, which are still in progress, by the way. And some of these tweaks are most akin to inefficient hacks than to universal upgrades. Well, these hacks are both frustrating and wonderful. They are responsible for our sieve-like memory, the errors we make when we perceive the world, and our snap judgments. But they also give us imagination, the delight of discovering illusions, and our uncanny ability to find patterns in everything. To understand the hacks that nature has applied to our brains, we need to consider our path through millions of years of evolution. But it's very difficult to find definitive evidence for the evolution of specific psychological traits or neuroanatomy. We can only make inferences based on what we can see. For some answers, we can also look to the brains and behaviors of other animals and to the similarities and differences between our fellow humans. But you have to be careful, because it is far too tempting to look to evolution for a good story and to be taken in by a compelling explanation that our minds developed just so. This type of thinking feeds the myth that natural selection had a design in mind all the while. But the reality is so far from that. When it comes to the adaptive but imperfect design of our brains, the material nature had to work with were cells. In the brain, these cells are called neurons. Our neurons point to the less than perfect process out of which the human brain emerged. Of course, natural selection is the process by which some traits which are written into our genetic code afford some advantage to those who possess them. These lucky people must then leave behind more children than their less gifted counterparts for the trait to proliferate. There's a lot of variability in our humankind, our brains, and all other regions as well. And without variability in a population, there is no opportunity for natural selection to operate. Imagine we were all the same. And of course, here we're talking about with respect to a particular trait. Then there's no way that Mother Nature can favor some people over others. They're just the same. How can Mother Nature select? How can natural selection even occur? So, our diversity is the key to the long-term survival of our species. This variability and diversity is evident even among neurons, the building blocks of our brains. Neurons have different sizes and shapes, different baseline firing rates, different types of connections, and different responses to the chemicals involved in cell signaling. And these chemicals, of course, are called neurotransmitters. So what about the neurons? You may remember that from biology classes, but if you don't, no problem. Neurons have three basic parts. Dendrites, which receive information, the cell body, which contains all the things the cell needs to survive and reproduce, and the axon, which sends information on to other cells. For some neurons, the receiving end interacts directly with the outside world, as is the case in our eyes. These types of neurons will generally have fairly simple receptive parts. But other neurons are not that simple. There are Purkinje cells in our cerebellum with dendrites like trees. When you look at the neuron's shape under a microscope, you see the cell's dendrites resemble a tree. It is too complex and too big. But it is needed because our cerebellum is responsible for coordinating different actions from different regions of the body, so it needs this kind of shape. So, the morphology, which is the size and shape of neurons, is one variable that evolution has to work with. The length of connections, that is how far or near a neuron signal goes, is another variable. Some neurons send information only over very short distances within the same brain region. Then there are neurons whose axons travel from one end of the brain to another, joining together different brain regions and forming networks that allow us to synthesize information from different senses or use information from our eyes and ears to make decisions about what to do next. This variability in our neurons and these differences are related to the different roles these neurons have in the brain. Some neurons distinguish colors from one another, while others power your muscles. Some are involved in complex cognition, such as deciding which political party to vote for, while others lie down new long-term memories. But a neuron cannot control what it does or does not do. This issue lies at the heart of one of the biggest philosophical questions. How does the mind, which gives us at least the feeling that we can control our actions, emerge from billions of cells that themselves have no control over their own actions? I know, it's a lot to take, and it is actually a philosophical question, but if you think about it, it kind of makes sense. So, how do we assume to have control, and our own neurons, our brain cells, do not have control over their own actions? So here's where we turn back to Mother Nature for the answers. Both the tiny local interneurons and the large complex neurons are found in other animals, such as monkeys and mice. And the cerebellum has an analog in most other animals with a nervous system. So the complexity of the human brain, although impressive, is an emergent property of the many, many small changes that occurred at every branch of our ancestral tree. And here, let's focus a little bit on evolution. Remember, we're still trying to figure out if this myth is true that our brains are perfectly designed. I'm going to hit you with it. They're not. So let's talk about it from an evolutionary point of view. There are a few different types of neurons that seem to play roles in functions such as fine motor coordination, social interactions, and self-awareness, but they are also present in other animals. And they might have arisen through successive tweaking of the basic neuron. Natural selection ended up with a hacked set of new cells, not a carefully designed foundation on which to build a perfect brain. Even so, when we consider the sophisticated way by which neurons communicate, it's once again difficult to imagine how they might have evolved from the single-celled organisms that were the very beginnings of life. How does a bacterium turn into a neuron? The answer is actually fairly simple. The stuff of cells is encased in a membrane. The membrane has to have certain properties, such as keeping mitochondria in and keeping unwanted toxins and foreign substances out. But it also has to have an opening or a way of letting in molecules that are desirable. Often, the inside of the cell has a slightly different electrical charge compared with the outside. In most cells, the inside contains more ions or negatively charged molecules than what's floating around outside the cell. This condition means that there is an electric potential across the cell membrane. Electrostatic forces are present, such as that positively charged things want to enter into the cell and negatively charged things want to leave the cell to bring equilibrium to the membrane. All living cells have different concentrations of ions inside them compared with what's just outside. But neurons and some other cells have harnessed the difference for some end goal. In the case of neurons, the goal, ultimately, is to send a signal to a nearby cell. If you open up a hole in the membrane of any cell, the stuff inside the cell can fall out. In the case of neurons, things that are negative will leak out and things that are positive will leak in, causing the electrical potential across that part of the membrane to depolarize or becomes less negative and more positive. This depolarization is at the heart of the way in which neurons talk to each other. Once the amount of depolarization crosses a certain threshold, it sets off a cascade of events in the cell that culminate with the sending of an action potential or a tiny electrical signal down the end of the axon. This signal then can either be transferred directly to another cell or it can cause another cascade of events that results in the release of neurotransmitters, which are the cell signaling chemicals into the space between one neuron and the next. So we can begin to see how any cell with a polarized membrane could eventually, over the course of many years and many incremental changes, turn into a fully functional neuron. Then once we have one kind of neuron, the others just represent different personality types. You might be willing to accept that this type of evolution explains how neurons came about, but still have trouble seeing how little hacks could lead to the emergence of all the complexity of the human brain. To understand how this might happen on a slightly larger scale, consider how self-awareness and identity develop in children. They're not born with the same self-consciousness that ultimately plagues their teenage years. And the process takes time and experience with the environment, not just some biological process in a vacuum. A baby is not conscious of itself or of its thoughts and feelings in the world around it the way that an adult or even a child is. Most of the changes that happen during childhood that differentiate a 1-year-old from an 18-year-old are in the connections between the neurons, not in their numbers. One of the signs of healthy brain development in childhood is the pruning or death of neurons that aren't finding the right connections. A neuron whose messages are sent into the void or one that isn't receiving sufficient signals commits suicide. By the time a brain is fully developed, there are no neurons that aren't part of some network because an isolated neuron dies. But from the perspective of a baby neuron, destiny seems quite random. What dictates whether a particular neuron will end up as part of the visual system at the back of the brain or the central executive in the prefrontal cortex or in the emotional salience network in the middle of the brain? The answer is in a combination of chemical signals and the scaffolding that the network of helper cells called glia builds. So neurons are not the only cells in the brain. In fact, there are about as many support cells in the brain as there are neurons, if not even more. This is another difference between the brain and most other organs. Many of the cells in our body are much more self-sufficient when compared with neurons, which are like celebrities. They need an entourage of assistants to help them with basic functions. But their talent is in signaling and ultimately producing thoughts, feelings, and other exceptional skills that our brains possess. All cells start off the same, as daughters of stem cells. And initially, as the brain grows, changes are rapid and seem to be almost left to chance. This might be true, or it might be that we don't know what factors cause one progenitor cell to become a neuron and another to become a support cell. But eventually, the rate of change slows and neurons find their places by sending out signals to their neighbors and figuring out who is willing to talk. And remember, those whose messages are not returned simply die. And of course, that is the micro level. But at the macro level, when we're thinking about how the connections across the brain get formed, this process is magnified. But you can still see how complex cognition emerges from simple processes. Brains develop and wire up with experience, and that's another way that diversity happens between different people and different brain regions, but this only happens gradually. So you can see that it is not actually perfectly designed. It's far from being perfectly designed. The wiring in our brains is actually highly contingent on environment and experience, and even on how our brains were used, stimulated, and developed in the past. And there's one more thing we need to talk about to completely debunk this myth that our brains are perfectly designed, and that has to do with noise. Now, in addition to being shaped by evolutionary tweaks and personal life experiences, another important factor actually, that makes our brains far from perfect is noise or randomness. For example, the random firing of action potentials. And you might say, what does that mean? Do our neurons just fire randomly? Well, actually, yes, they do. Neurons have a baseline firing rate. They send out random signals that don't actually carry meaning, at least no meaning that we've been able to discover so far. And most of the energy used by the brain goes toward maintaining the electric potential across the cell membrane so that this firing is possible. We think of the action potential as the result of a summation of incoming signals from other cells. But the truth is that action potentials are randomly fired off all the time. And the signal then, which is the meaningful message, is a change from this baseline firing. So a huge amount of energy goes into this constant baseline firing, but the firing itself doesn't necessarily mean anything. It's only a change that carries meaning. So most of the energy the brain consumes sustains an essentially random and meaningless activity. Yet this randomness is also the base material that gets molded into a mind, both by Mother Nature, tinkering over millions of years, and by our own experiences over the course of a lifetime. And maybe this random firing, if you think about it, is what gives birth to imagination, which is random, which is not expected. Maybe, I'm not saying that this is the answer, of course not. There's no evidence whatsoever that imagination comes from this random baseline firing, not at all. But I'm just saying, what if? What if the special thing about us as humans, our imagination, is the result of this random firing? But anyway, that makes us, or actually makes our brains, imperfect. And now, of course, a little bit away from science, maybe the most beautiful thing in our brains that they are not perfect. I mean, if we had perfect brains, maybe we would be like machines. Who knows? So just to wrap up, we talked about the myth that your brain is perfectly designed. That's the myth, but the truth is different from that. Well, actually, the brain is a product of evolution. The brain is shaped by natural selection and includes many inefficient hacks. And that was our very first myth in our Brain Myth series. I know that there's a lot of science, but trust me, there's not enough science in what I'm putting here. And this is just kind of like using layman terms so that we all understand, and so that I understand in the first place. Because remember, yes, I'm crazy about the brain and neuroscience, but I'm definitely not an expert. I'm just an avid learner, that's all. So that was our very first myth. Next, we're going to talk about the size of the brain. And our very next myth or question, are bigger brains smarter? What do you think? Now, of course, because you know that we're talking about myths, you're going to say no. But think about it in a different context. Before you listen to brain myths, if anybody asks you this question, is bigger brain smarter? You may say yes, you may say no. But do you know why? Well, that's what we're going to talk about next. So don't go anywhere. I'll be right back. Intelligence remains difficult to measure and next to impossible to define. Yet many people intuitively believe that people with bigger brains are smarter. Now, I have to admit, there is a moderate correlation between human brain size and many measures of intelligence, and that means the bigger a person's brain, the better he or she will perform on average on, for example, IQ tests. But remember, this correlation is only moderate, and there are many other factors to consider. So, are bigger brains smarter? Let's find out. Compared with many other species, humans are born with fairly small brains, leaving infants pretty much defenseless and unable to survive without a lot of care and attention, at least for the first year. Wouldn't it make more sense from the perspective of our own chances of surviving long enough to reproduce if we were born with more developed brains, making us at least capable of feeding ourselves, if not avoiding being eaten? Well, to explain this conundrum, many people point to what's the obstetrical dilemma, which is the problem that walking upright supposedly created. A long-held idea is that during our evolution, there was a selection pressure for a smaller pelvis to help us walk upright, which was then at odds with the selection pressure to house a bigger brain in newborns, whose heads have to pass through a woman's pelvis. The smaller the pelvis, the better able we are to walk, but the smaller the opening for a baby's head. This dilemma is used to explain why human babies are born rather underdeveloped. This explanation also purports to tell us why brain size triples in the first year and why the skull of a newborn has soft spots and cracks in it, enabling it to fold and squeeze through a small birth canal without damaging the brain encased within it, but leaves the baby vulnerable to grave injury until the skull closes and toughens up. But new research is calling this view into question. Compared to other primates, our babies aren't really born prematurely. Other primate infants are also pretty dependent on their parents for a while after birth. And there's no evidence that a larger pelvis in women would interfere with walking or any of the other things we use our pelvis for. So if it really was just about bigger brains, mothers would just develop wider hips. But the story of brain development is much more complicated than that. Instead, evidence is mounting that our gestation time is limited by the amount of food that a mother can supply to herself and her baby. And around the 40-week mark, this limit is reached. She simply can't get enough energy from food to fuel a growing baby and herself. If you stand behind the argument that a bigger brain means more intelligence, then you're going to have to concede the prize for most intelligent animals to whales, with elephants not far behind. But then you might think that this is not fair. The whale's body is much bigger, so it must have big brain. Why don't we quantify this as the ratio of brain size to body size, and then we can decide if humans have the bigger brains in the animal kingdom? Well, if you think about it this way, humans clock in at about 1 to 40, which is actually the same ratio as a mouse. But there is a number that might, in fact, matter, and that is the encephalization quotient, which is the ratio of the actual brain mass over the expected brain mass of an organism with the same body mass. I know it's complicated, but you will see that this is also not a big deal. Anyway, the ratio takes into account the fact that bigger bodies are expected to house bigger brains, but our brains are quite a bit bigger than the brains of the other mammals who are about the same size. The lowly mouse looks fairly stupid, and humans do come out on top, beating dolphins, whales, and elephants by a fair margin. So maybe if we take this number into account, maybe our brains are bigger, that's why we're smarter, etc., etc. But wait.
Stay with us. We'll be right back.
Looking to enhance your English skills while exploring a world of knowledge? Then English Plus Podcast website is just for you. Dive into diverse topics ranging from science to literature, history to business, and myths to modern insights. Each episode from our podcast or article from our magazine is a journey of learning and discovery, designed to not only improve your language skills, but also broaden your understanding of the world. Join us at English Plus Podcast, where language meets limitless learning. Tune in today and take your English to the next level. Visit EnglishPlusPodcast.com to start your journey. English Plus Podcast, language, learning, enlightenment. Never stop learning with English Plus. Don't jump to conclusions yet. We might be tempted to go for the easy answer, but unfortunately there are no easy answers when it comes to brain. And that's why we try to dive in a little deep into science, to try and understand this from a scientific point of view, not just trying to give anecdotal evidence to these big questions or big brain myths. So to understand this a little bit more, let's think about measuring intelligence. Consider the notion that there exists some kind of measurable general intelligence. Figuring out what it is and whether and how it can be developed or enhanced is a billion-dollar question that psychologists have been trying to answer for decades. The G factor, or the general factor, is what many psychologists have spent entire careers searching for. The idea is that there is a common factor that correlates with performance on a wide array of tests of cognitive abilities. If someone is very good at math, he or she is also likely to do well on other tests of intelligence such as vocabulary and reading comprehension. And there's a fair amount of evidence supporting this idea. Now, most studies show that the G factor accounts for about 40 to 50% of the variability between subjects on IQ tests. And it seems that G is highly heritable. It can predict with fairly decent accuracy how well a child will do in school and how far they will get in their careers. And it correlates with total brain volume, though only moderately so. That means that a significant portion of the variability in this general intelligence factor has nothing to do with the size of your brain. Height is also associated with G, so taller people might be smarter on average given their bigger brains. Once the G factor was suggested and fairly widely accepted, it was further divided into two types: fluid intelligence and crystallized intelligence. You can think of them as the difference between quick thinking and wisdom. Fluid intelligence peaks in your 20s, while crystallized intelligence remains steady, or actually it steadily increases throughout adulthood. Of course, but all that depends on how you use your brain. But despite the evidence for the existence of a G factor, whether fluid or crystallized, not all psychologists are happy with the notion that there is one major underlying ability. Perhaps the most famous challenge to G is Howard Gardner's multiple intelligences theory, which considers the soft skills such as social graces that might not be captured on traditional IQ tests. In his theory, Gardner suggests that there is no single factor, but that intelligence comes in many kinds, including musical intelligence, visuospatial, verbal linguistic, logical mathematical, bodily kinesthetic, and so on. Gardner's theory caught on quickly, but despite the intuitive attractiveness of the idea, the evidence supporting his theory is slim to non-existent. So then how can we find out about this? And it's kind of difficult to just go inside human brains to figure out these answers. Now, of course, all the studies were done on dead brains, not on alive brains, of course, unless we're talking about some crazy scientists out there that nobody knows about. But anyway, what about if we could do something like this on people we already know, or actually we already agree that these are intelligent people? Say Einstein, for example. Now, luckily for science, Albert Einstein's brain was saved for post-mortem analysis. Now, since we're going to talk about Einstein's brain, of course, we can all agree that at least this man is intelligent. So let's look inside his brain and let's see if we can find some answers, some G factor or whatever factor that can tell us why this person is smarter than other people and how we can measure this thing or maybe even enhance it in the future. So back to Einstein's brain. At least in 4 different sections of his brain, and at least compared with a certain cohort of war veterans, the ratio of neurons to glial cells, and remember the glial cells, these are the cells that provide the neurons with the basic necessities of life and ensure that they can concentrate on firing off or not a signal. So, what about this ratio? Well, actually, the ratio of neurons to glial cells in Einstein's brain was found to be lower than in his veteran counterparts. However, this ratio difference was only significant in one of the 4 brain sections studied, and the researchers conducting the analysis knew which slices belonged to Einstein and which belonged to the vets, so maybe they were unconsciously influenced to find differences. In addition, there's a paper in which the lower neuron to glia ratio in the left parietal region is used as an explanation for Einstein's purported dyslexia. Even more than that, research on a section from Einstein's prefrontal cortex, which is responsible for complex cognition, shows that his cortex was thinner, but that the neurons there were more densely packed. In many studies, cortical thickness is taken to be a good thing, and aging and neurodegenerative diseases can cause cortical thinning. Maybe more densely packed neurons gave Einstein an intellectual edge. Perhaps neurons that are close together can communicate more quickly and efficiently with each other. However, people with schizophrenia have also been shown to have more densely packed neurons in the prefrontal cortex. So, unfortunately, that hasn't answered any questions. So let's dive in a little bit deeper and look at the composition of brain regions. Now, if overall size is not the answer, maybe it's the composition of specific brain regions though, those that are important for the types of thinking that IQ tests measure. And there are plenty of studies that have found correlations between different aspects of neuroanatomy and IQ test performance. Broadly, these studies can be divided into two types. Those that measure differences in gray matter, and gray matter roughly translates into the number of neurons, and there's also the white matter, and these are the connections between the neurons. Now, gray matter in the frontal lobes does correlate with intelligence, as measured by IQ tests at least. For example, spatial tasks and verbal tasks are thought to rely heavily on the G factor, and they seem to activate or rely on a set of regions in the front of the brain. Apparently, the more gray matter that is in these regions, the better the performance is on these particular tasks. And there's evidence from patients with brain damage or deterioration of gray matter in the frontal cortex that demonstrates how important this region is when it comes to behaving intelligently. Patients with damage to the region tend to show worse performance on intelligence tests and make bad decisions in daily life. So maybe size does matter when it comes to the frontal lobes, though the story is quite complicated. It gets even more murky when we start to consider that the frontal cortex doesn't act in a vacuum and that the real work of the brain happens between neurons, not within them. This is where white matter comes in. White matter represents the connections between neurons. How much white matter you have might be an indicator of how well and how quickly your neurons can communicate with each other. Scientists who study the relationship between white matter and intelligence say that they are investigating the neural correlates of quick thinking. The idea is that a person with more white matter does, in fact, think more quickly than someone with impoverished connectivity. And the faster speed of thinking then translates to greater intelligence. Indeed, we can find correlations between the amount of white matter a person has and how he or she scores on intelligence tests. The corpus callosum, which is the largest tract of white matter in the brain, connects the left and right hemispheres, and a larger callosum correlates with better performance on a range of cognitive tests, though not all measures of callosal volume have shown statistically significant effects. Some neuroscientists take this mixed evidence as suggestive of the idea that gray matter may be more important when it comes to defining the neural basis of intelligence. So you see, we don't have easy answers. Maybe it's a myth, maybe the question is difficult because we still don't know. And let's admit, we don't know a lot about the brain. I mean, we're just beginning to scratch the surface of how this organ works. But so far, well, the idea that bigger brains are smarter is not actually sound enough. So let's continue. Talk about our special brains, right? There's a Brazilian neuroscientist who's called Susana Husel. She devised a way of counting the cells in the brain that has called into question the very idea that our brains are special. In fact, she argues that the endurance of the encephalization quotient might have more to do with confirmation bias than with any real evidence because it's the one measure of intelligence that makes our species an outlier. And for those of you who don't know what confirmation bias means, well, it is simply a common mistake a lot of researchers do. Maybe not on purpose, but this is our nature. When we're trying to find proof to some theory we have, we actually try to find evidence. We try to confirm our theories with evidence in patterns that might not always be scientifically found. But we just find something that can prove our own thesis, so we just take it and we say that, yeah, this is the answer. And sometimes, in this case, we have what we call the confirmation bias. Not because we are biased by nature or something, no, but we are biased because we want to prove this. We need to prove this. I mean, how difficult could it be when you just spend years researching something and then after years of researching, you have to admit that there is no proof? So that might lead to this confirmation bias. And of course, that's what famous Brazilian neuroscientist Susana Husel said. What Susana suggests is that it might not be that we have bigger brains compared with our primate cousins, but that they have bigger bodies than we do. That is, maybe we didn't evolve bigger brains, but our primate cousins evolved bigger bodies, and their brains stayed the same size or even became smaller. And Susana Husel has shown that larger brains don't even necessarily mean more neurons. A primate brain that is the same size as a rodent brain will contain many more neurons. Susanna Hozel devised a model that predicts how many neurons and support cells a primate brain of a certain size should contain. Her model predicts that if we were just the logical next step on the evolutionary path, our brains should contain about 93 billion neurons and about 112 billion glial cells. The average human brain has about 86 billion neurons and 85 billion non-neuronal cells. Our primate cousins, the great apes, have smaller brains than their body size would predict because neurons are expensive from an energy use perspective, and gorillas and chimpanzees simply can't get enough fuel from their food to power more brain cells than they have. Once again, food might explain why babies are born with small brains. Perhaps the reason we can handle our big brains is because we figured out how to cook. Cooking our food freed up time to do all the other things that ultimately have shaped our brains into the sophisticated thinking machines that they are today. Susanna's work puts the nail in the coffin of the idea that brain size or the encephalization quotient even matters. But her work does help us answer the question of what makes us special. Now that we can get all the calories we need from cooked food, we can spend time shaping our average primate brains into powerful thinking machines. But Susanna Hozel cautions against applying this method to predict the number of neurons individuals in a species might possess. Her work has shown that intraspecies variability in the density of neurons is considerable and doesn't correlate strongly with brain size. So again, what was the myth we talked about? The myth is the bigger the brain, the better. But the truth tells us that intelligence and brain size, even in humans, are only moderately correlated. When you look across species, the correlation is even smaller. So this is another myth we have in today's episode. And with this, we come to the end of today's episode. We talked about 2 myths for today, and we debunked 2 myths. Is your brain perfectly designed? Not at all. Are bigger brains smarter? Well, not all the time. And these were the very first 2 myths in our series, Brain Myths, that we're going to have every week. So stay tuned, come back next week, and don't forget that we have a lot of other series, and we even have more series when you become a patron, because you will catch all the premium series that we have. You can benefit from all of these, and some of these premium series focus on language learning, of course. We will talk a lot about that in our Plus Talk episode at the end of the week, so you will have a better idea of the whole program. But enough being said for one day. Let me just remind you one more time that you can find the transcript of this episode on my website. The link is in the show notes. You can take the link, and while you're on the website, you can explore and see the many learning opportunities you can find on the website. Never stop learning with English Plus Podcast. Thank you very much for listening to another episode from English Plus Podcast. This is your host, Danny. I will see you next time.